Hi there, it's Paul, and I hope to illustrate for you some of the key concepts about infinite sequences and their limits using graphical displays in R. So let's first think about how we could represent an infinite sequence in R. Vectors in R are good for representing finite sequences, but a vector can't have an infinite number of components. We do better conceptually to use a function that takes any of the natural numbers and converts it into the corresponding element of the sequence. So I've written a function that generates the number n minus 1 over 2n plus 3. And I will give that a name. And now I can generate a vector that contains some of the elements of that infinite sequence. I'll do the ones from 10 through 100 inclusive. Any number of terms at the beginning of an infinite sequence are ultimately irrelevant, and the ones between 1 and 9 are small enough to mess up our display a little bit. So you can look at these numbers. It doesn't tell you too much, but it's clear they're getting bigger and bigger, and you might guess that the limit is going to be 0.5. A plot shows this much better. You can see these numbers getting bigger and bigger, closer and closer to 0.5, and there is a horizontal line at the position of the limit. Now, how will we prove that the limit is 0.5? What we do is specify a quantity which is traditionally called epsilon. I'm going to start with 0.05, and I'm going to draw red lines, one of them epsilon below the limit, the other one epsilon above the limit. Now, if you look at what's happening with these numbers, you see that they start out outside the red band, but eventually they get inside and stay inside. And it looks as though, starting about at the 25th element, they get inside and stay inside. I can draw a vertical line there. And now you see, for all little n that are greater than that capital N, the difference between the limit of 0.5 and the element of the sequence is less than epsilon. Now that was just with one epsilon. We could choose a smaller epsilon, like 0.03. That gives us a smaller red band, and off the graph it's fairly easy to see that if I choose a larger n, 45 for example, then if I go beyond the 45th element, again, all the remaining infinite number of elements of the sequence appear to be in between the two dashed red lines. No amount of graphing, of course, can prove that the limit of this sequence is the number s, 0.5. Instead, what I have to do is find a formula that automates the process I've been carrying out. Starting with an epsilon, it produces a satisfactory n. I went offline, did a little bit of algebra, and came up with the function that takes 5 divided by 4 times epsilon. You can check that calculation for yourself. And I'll try that out with a still smaller epsilon, 0.02. Now my dotted red lines define an even narrower band around the green line that represents the limit. I'll use my n-value function to compute an appropriate capital N, put a vertical line there, and it looks as though I've got it right. If I go to the right of that vertical line, all the elements of the sequence are within my narrow band. And in order to turn this into a formal proof, what I have to show is that if I choose a little n larger than the number calculated by my n-value function, then the nth element of the sequence is within epsilon of the limit. Now let's use this idea to prove a theorem about limits of sequences. Namely, if you sum two sequences term by term, the limit of the sum is the sum of the limits. I can't really do a proof in R, but I think I can illustrate rather nicely the strategy behind the proof by looking at a specific epsilon. So I'm now going to define a second sequence, the sequence t sub n. I'll first define it by a function, 3n minus 5 over 4n plus 1. I'll crank out a few elements of the sequence, and again you see it's increasing, and this time maybe the limit is 3/4. Now I will construct the sum of the two sequences, which I do by adding together the two functions that define them. That makes it possible for me to crank out some elements of the sum of the two sequences. And when I look at that, big surprise, it looks as though we're approaching a limit of 5/4, the sum of the two limits. Let's look at this graphically. There are the vectors, the numbers in the sequence S. Unfortunately, at this screen resolution, there's an awful lot of duplicates, which doesn't happen with the real data. Here are the corresponding elements of the T sequence, and finally the corresponding elements of the sum sequence. I have plotted a horizontal line at the position of the limit for the sum sequence, and what I want to show is that the height of that green line really is the limit. How do we do that? We pick an epsilon. I've chosen 0.06 and drawn a little band, 0.06, on either side of the green line. Now comes the clever part. I'm going to allocate half of that epsilon to the S sequence and half to the T sequence. So I'll define a new variable, eps2, which is epsilon over 2. I will look down at my S sequence, where we already know that the limit is 1/2, and I will draw a band on either side of that using my smaller epsilon, half the original epsilon. And what I see when I do that is at n equals 42, I appear to get inside that band and stay there. So for the S sequence, 42 does the job. Now I do exactly the same thing with the T sequence. And on inspecting the display, it looks to me as though if I use a number that's bigger than 55, I'm safely inside the band for the T sequence. Now that 55 is also going to do the job for S plus T. If I go beyond the 55th element of the sum sequence, then I can be sure that my S value won't be more than half of epsilon away from its limit. The T value won't be more than half of epsilon away from its limit, and therefore the sum of the two has to be within epsilon of my limit for the sum of the sequence S plus T. And in order to turn this into a formal proof, all I have to do is to argue that this approach works not only for examples, but for any positive epsilon. When you do this, you'll discover that it's arguably easier to write out the general proof than it is to look at specific examples. But I think that I at least find that visualizing this graphically is a great help in inventing the proof. Now for the last topic, we're going to do your second proof for this week, proof 5.2. This is proving that if you have the inverse of a sequence, that is, the sequence that you make by turning each element into its inverse, and furthermore, no element of the sequence is ever 0, because 0 has no inverse, and finally, that even though this sequence may contain both positive and negative elements, the limit of the sequence is a positive number S. This argument is equally valid for a negative value of S, and in Ross's textbook it's done for S of either sign, but it's easier to visualize if we consider the special case where the limit is positive. Now I'm going to define a sequence that has some randomness built into it. I'll start with 0.1. That's going to ultimately specify the limit of the sequence. And then I'll add on 1 over n plus 2, so we'll sort of sneak up on this from above. But I'm going to add in a bunch of noise. I'm going to add in a random value that can range anywhere from minus 4 over n plus 2 to plus 4 over n plus 2. And when I generate 100 numbers in accordance with that, I look at them, and some of the numbers will turn out to be negative. You can see it looks as though the fourth one is negative, the seventh and eighth ones are negative, and so on. It's much easier to visualize this sort of thing with a plot. So let's plot this sequence. And this is really looking a little more interesting than the other ones, right? This is looking like real-world data. The numbers do appear to be converging on 0.1, but not in such a systematic way. Now let's look at the sequence of inverses. So I will create an empty vector with 100 components, and I will populate it by taking 1 over the value of my original sequence. And when I plot that, I discover that some of the values are positive, some of the values are negative, but it is plausible at least that the limit is 10. That as I go farther and farther to the right, these numbers are settling down around the inverse of the limit 1/10 of my original sequence. If I want to go further along, I can't plot every single point, but I can define in R a sequence that basically counts to 500 by 5s. And if I use that sequence and plot it, then my original sequence appears to be zeroing in nicely on 0.1, while my sequence of inverses appears to be zeroing in on 10. Now let's consider how to do the proof. It turns out to be very important to be able to set a lower limit on S sub n. Now you say, I can't do that. Some of those were negative. Ah, yes, but if I go far enough along, S sub n has to get closer and closer to the limit. And in particular, I can go far enough along so that S sub n must be at least half the original limiting value. I actually worked this out by calculating from my formula, but if you look at a plot of this, you can see that if I want to get above that red line and stay there, that is, if I want to get above 0.05, if I go out to the 58th term and beyond, I'm safely there. So beyond that point, I can say that S sub n has to be greater than the limit S divided by 2. Now what do I need to do in order to prove that the sequence of inverses converges? I have to show that the difference between the nth term, t sub n, and the limit t can be made less than some epsilon that you give me. And with some very elementary algebra, this is done in ROS, and you can do it yourself by hand if you like. You can show that if I make S sub n minus s less than epsilon times s squared over 2, that will do the job. In getting that s squared over 2, I have actually replaced in the inequality s sub n by s over 2. So this is valid only when we're beyond the 58th term. Only once we're sure that no term in the sequence can ever be larger than 1/2 the limit. For my epsilon, I'm going to pick 2. That doesn't seem very small, but it turns out that with 500 terms, that's about as close as I'm going to be able to get. So what I want to show you is that by going far enough along in the sequence, I can make all the t sub little n's be within epsilon of the limit of 10. And the way I do that is by calculating what epsilon I have to supply for my original sequence. What I do is take the epsilon I was given, 2, and multiply by s squared over 2 by 0.01 divided by 2, and that quantity works out to be 0.01. Now let's look at what we've got. There is my original sequence, and here is a narrow band within epsilon on either side of the limit. And if you look at that, you'll notice that at about n equals 400, I seem to get inside that band and stay there. The only thing that ultimately matters is that some such n exists. And if I'd chosen to say n equals 1,000, that would be equally good for purposes of doing the proof. So I draw that blue vertical line and say, to the right of the vertical line, all the elements in the S sequence are within that band. Now I go back to my sequence of inverses and plot that. And again, with my given epsilon, I use a vertical line at n equals 400. And it had to work this way because my algebra was correct. As long as I go beyond the 400th element of the sequence, I'm guaranteed to be within epsilon of the limit. This argument is easily converted into a general proof, and yet again, the general proof will turn out to be easier than the example, for the simple reason that we're not considering a specific sequence. We don't have to cite specific values for n. All we have to say is, knowing that the original sequence converges, I can figure out an appropriate epsilon, figure out an appropriate n, and that n will work for the sequence of inverses.